All right, so today we are going to start looking at chapter 6. Okay, and this also starts kind of the next big section of the class, which is on trigonometry. Okay, so first we'll just kind of take a look at that, see if we can break down that word, figure out what it means, and then I'll give you a couple examples of things that we do in trig. So looking at the word trigonometry, does anybody recognize any part of the word? Yeah?
Try.
Yeah. What's try mean?
3.
3. Okay, so try means 3. Is there anything else there that people recognize in that word? Yeah.
Geometry, like geometry, that kind of stuff.
Okay, so that suffix matri, that means something. Anybody know what that means?
Is it like the study of it or something like that? What's the...
Not study of. Study of is ology. Yeah. So study of is ology, biology, psychology, things like that. But anyone have another thought what matri means? Does it kind of, yep.
Is it like numbers related?
Yeah, it does have something to do with using numbers to do something. Yeah. Measurement, yeah, measurement. So geometry, trigonometry, those are two subjects that end in matri, so something with measurement. And how about gone? What does gone mean? Anybody think of a word in math that has gone in it? Hexagon. Yeah. Polygon. Yeah. So what do you think? Circle. Oh, circle doesn't have gone in it.
That doesn't mean like something to do with circle.
Oh, something to do with a circle. No, it does not mean something to do with a circle. Yes?
Does it mean like side or something like that?
Sides. Yeah, sided.
Circle does not have God.
So, yeah, I thought that's what you meant. Hexagon, right? 6-sided. Pentagon, 5-sided. Trigon, 3-sided. So, trigon is another name for a triangle. Every two-dimensional shape has a name that ends in gon. We normally use the name triangle, but trigon is another name. Tetragon, it's a 4-sided shape. We normally say quadrilateral, but you can say tetragon, 4-sided. Most other shapes above 4, we naturally just use the name ending in gon. Pentagon, hexagon, things like that. So 3-sided measurement. So we're going to be dealing a lot with triangles and trying to measure something in them to figure out our problem. Triangles have angles and they have sides. So depending on what we want to know, we might be measuring one or the other. So let's say we had, just as an example, something like this. And we got a building over here at a 90-degree angle and a person standing over here. And let's say that person knows how far they are from the building. They're 500 feet away. And from where they're standing, they measure the angle to the top of the building, which is pretty easy to do if you have just like a piece of string and a protractor. You can just hang a little weight on it. As you tilt it, the string always hangs perpendicular, but the protractor will turn and it'll tell you the angle that you're looking at. So it's a kind of a real simple way to make a device that can measure what's called an angle of elevation. So let's say you measure that angle and it comes out to like 30 degrees. If you know the angle that you're looking at something and how far away you are, you can find the height of it. And we're not going to get into it today, but it comes down to making a triangle, just like that, and then solving for the height of that purple triangle with the information that you're given. So that's an example of something you could do with trig. Here's another example. let's say that there was 2 towers. We've got 2 towers, one here, and we got another one over here. And somewhere in the distance that they see maybe some smoke or a fire far away. And they want to try to figure out where that fire is. Okay? Maybe they want to figure out, I don't know, you're going to program a drone to drop water on it or something. They need to know the coordinates of where the fire is. Well, as long as you know how far apart these two, just to make it simple, let me put this lined up with the other one. As long as you know how far apart those 2 towers are, which that's easy to figure out because if there's somebody in each tower, they could use GPS to figure out exactly what their location is. So you can find out how far apart the 2 towers are. And then if each tower can see the smoke, they don't know how far away it is, but they do know the direction they can see it. Okay, so like this tower can say, I see the smoke coming at this direction. You just look at a compass and it'll tell you what direction it is. And the same with this tower. Okay. Again, they could see the smoke, but they just can't tell how far away it is, whether it's 5 miles, 6 miles, 4.5 miles. Right? That makes a big difference if you're trying to target a certain area to drop water or whatever they do to put the fire out. But working together, each of these towers has a line of sight on the fire, and we just made a triangle right here. Okay, the difference with this triangle, it's not necessarily a right angle. Okay, there could be a right angle, maybe not a right angle. This one above, we were guaranteed a right angle because the building was perpendicular to the ground. All right? But that's an example of what we call triangulation. Okay? You can triangulate where something is as long as 2 different people can see that object from different points. So that's kind of how GPS works. You can triangulate where you are because multiple satellites can see your position. If only one satellite could see your position, you can't really get a location. You need multiple. And the more you have, the better it works. Okay, so there's a couple different things we can do with trig. So different things in this triangle we'll talk about are the sides. Okay, there's always 3 in a triangle, and the angles. Today we're going to start talking about just the angles. So we'll talk about the names of different kinds of angles, like what it means to be obtuse, pairs of angles, like complementary, supplementary. We'll also talk about how you can measure angles. There's a couple ways. One of them is degrees, but there is a second way that we'll talk about. Let me see, actually, we're going to get to that today. Yes, that'll be the last thing we do. So start out with what is an angle? Well, if you're drawing an angle all by itself, then an angle is made up of 2 rays, and the rays have to start at a common point that we call the vertex. So there's an example of an angle right up there. 2 rays with a strong common starting point called the vertex. When you have an angle, it has 2 sides to it, and we call them the initial side and the terminal side. Does anybody have a guess which side is the initial side in that angle? Just make them different colors so you can reference the color. Yeah. The red one is the... Yeah, the first one, the initial side. Yeah, the red side is what we would call the initial, and the black side is what we would call the terminal. And the way we can figure out which side is which, if you're not sure, if you have an angle like that, and you are between the angles, okay, not on the outside, inside. If you rotate counterclockwise, like this, between the two rays, the side that you start at is the initial, and the side you end at is the terminal. So initial, terminal. And it doesn't matter how you rotate that. I can take this picture and I can group these together. And I can rotate them any way that I want. The red side is always the initial, and the black side is always the terminal. Okay, even if I do it like that. Initial, terminal. So again, that's rotating in a counterclockwise direction. CCW, counterclockwise. To get from the initial to the terminal. So there are different ways that we can rotate. We can rotate in a counterclockwise direction. And what do you think the other direction would be? Yep.
Clockwise.
Clockwise. And the direction that you rotate when you're measuring an angle is going to control whether it's positive or negative. So let me show you a picture of that. All right, so here's a program where I can draw different angles. The initial side is horizontal, and the terminal side, that's the only side that I can move. But as I rotate counterclockwise, you'll notice the angle is positive. If I put it back at 0, and I start rotating in a clockwise direction, now I'm getting a negative angle. Okay, so whether you have a positive or a negative angle, it just controls the direction of rotation if you're moving on a circle. When you're talking about an angle inside of a triangle, then no, you'd never have a negative angle. Because in a triangle, we're not using an angle to describe an amount of rotation. Right? So there's really two things you can use an angle for. How much did you rotate, or how big is an angle inside of a shape? So when we don't know an angle, a lot of times we use a Greek letter to represent it. Just like in algebra, we use x quite a bit. When we don't know something, well, Greek letters are what we're going to use for angles. Bless you. The reason we don't use English letters for angles is because we already use English letters for something else in a triangle. We use them for the sides. Think of Pythagorean theorem. What are the letters most commonly used in Pythagorean theorem? A, B, and C. Yep. So we already use those for the sides. We don't want to use them for angles. So let's go through, just make sure we know the names of these. That first angle, does anybody know the name of fish? That one? Looks kind of like a fish. Fish. It's the first Greek letter, and it's a lowercase. Yeah.
Oh.
Yeah, that's alpha. So there's alpha. How about the second? Greek. Yep, and these are all lowercase. There are capitals as well, but we don't use too many capital Greek letters in trig. They're used in other places, but we don't use them too much. How about this third one? Anyone know that one?
Charlie.
Rhymes with grandma? Yeah? Yeah? Gamma, yeah. So we got gamma. So when we have to describe three angles at the same time, these are generally the letters that we go to. Just like A, B, and C for the sides, alpha, beta, gamma for the angles. when you have to describe a single angle by itself, just one angle, that's the Greek letter we use a lot. Anybody remember that Greek letter? Yep.
Is that theta?
That's theta. And the last one, sometimes we see that when we're talking about graphing trig functions, and it's used to modify horizontally stretching and compressing the graph. Anybody know that last letter? It's the lowercase version of this letter. Yep.
Omega?
Omega. Yep. That's omega.
Curious, how do people know this?
Okay. So those are the 5 Greek letters that we'll use. The first 4 quite a bit. The last one, sometimes, it depends. All right, so we'd like to be able to draw angles in a way that everybody's kind of looks the same. So like, if I said to draw a 90-degree angle, you should be drawing something like that. Now, technically, that's a 90-degree angle as well, but it's kind of turned. Standard position is going to give us a way that if I ask you to draw any kind of angle, everybody's just going to look pretty much the same. So when you draw an angle in what's called standard position, you have to do 2 things. One, you have to put the vertex of your angle at the origin. And 2, make sure the initial side is on the positive x-axis. This also makes it easier to figure out the initial and the terminal. Because now we're going to know if it's in standard position, the initial side is always the horizontal on the positive x-axis. So that angle in red, that is an angle in what we would call standard position. How about if I did this? Is that still in standard position? No, Boris, what's wrong with that?
It's not at the origin?
Yeah, the vertex isn't at the origin. The initial side is definitely on the positive x-axis, but it wasn't at the origin. How about if I did something like that? Is that standard position? No. The vertex is at the origin, but what's wrong this time?
It's not on the x-axis, positive x-axis.
Say it again.
It's not on the positive x-axis.
What do you mean it's not on the positive
It's
x-axis?
not like touching it. It's not like laying on it.
What's not?
Oh, the line. The initial side?
The initial side, yeah, is not on the positive x-axis. The terminal side looks like it's on the y-axis, but that doesn't mean anything. So we need it just like that for standard position. All right, so any questions on that? So one way that we can measure an angle is in degrees. And if you looked at this program as I was using it, the top number is degrees. And we know that because it puts a little circle on it. Anybody know what the bottom number is? So we're going to talk about that bottom number later today. And that's going to be very important for like everything we do in trig.
Is it a measurement?
It's a measurement. Yep. Yep. So we'll look at that in a little bit. If I were to go all the way around that circle, how many degrees would it be all the way around if we go counterclockwise? Yep.
360.
Right. If we go all the way around, it shows us 360. Yep. It also shows us this 2 pi. We'll come back to that. Okay, 2 pi. But 360 degrees is one full counterclockwise revolution. How about a half counterclockwise revolution? Yep.
180.
So yep, that would be 180. And what about a quarter counterclockwise revolution? Yep.
90.
90. So notice each time I said counterclockwise. If you go counterclockwise when you measure an angle, then that is positive. And we said if you go clockwise, then the angle would be negative. Yep. Again, negative angles are only used in the context of talking about rotation about a circle. They're not used inside of shapes. Is there any question on the difference between a positive angle and a negative angle? We also can get angles that are larger than 360. And if you have an angle larger than 360, in terms of rotation, it means you've gone around more than one time. So if I take this and I keep going past 360, then the angle just keeps going. So anything bigger than 360 means we've gone around more than once. Same thing if you go less than negative 360. At negative 360, you've gone around one time. Now if you keep going, you're going past negative 360, because you've gone around more than once. Yes?
Is the bottom number the radius or the radii?
It has something to kind of do with that, but the radius of the circle is fixed. The size of the circle is not changing. But we'll talk more about that. But yep, it has something to kind of do with that.
Is that the length of the red line, is it?
No, it's a measure of rotation. It's not the length of a line. It's a measure of rotation, just like the top number. It's a measure of rotation. So I want you to look at this angle, okay, 90 degrees, and I just want you to look at where the initial and where the terminal sides are right now. Now I'm going to go like this. How do the initial and the terminal sides now compare to where they were at 90? Yeah, it's the same. Now I want you to look at 810. How do the initial and terminal sides compare now to where they were at 90 and 450? Still the same. So we had three different numbers that I just did: 90, 450, and 810. All of those three angles had the same initial and terminal sides when I drew them. Okay, everybody agrees with that? Mm-hmm. Okay. So let me type in the cosine of 90. Okay, what I got? I got 0. Okay, we don't know too much about cosine yet. I just want you to look at a pattern here. Let's do the cosine of 450. 0. Cosine of 810. What do you think that's going to be?
0.
That's also 0. If you have two angles with the same initial and terminal sides, like these three, then when you press one of these three buttons, sine, cosine, or tangent, you're going to get the same answer for each one. Okay? So
What
like
would
if
you
I
get if you put in a random number?
So like sine 90, I get 1. The other ones are going to have the exact same sign. 450 and 810. So you can't just pick any random number here. 90, 450, and 810 are very specific. There's other ones, but the key is to look at how do you get from 90 to 450, and how would you get from 450 to 810? Add 360, yes. So anytime you add or subtract 360, you are finding what's called a coterminal angle. A coterminal angle has the same initial and terminal sides as another angle. But the advantage of a coterminal angle is it can be easier to work with than the given angle. So let's say I gave you an angle like 1,560 degrees, and I ask you to do something with it. Well, have you gone around the circle more than once if you're dealing with 1,560 degrees?
Mm-hmm.
Yeah, that's going to make it complicated to figure out where the initial and the terminal sides are, which we do need to figure out when we're going to work with this angle. So then, don't work with 1,560 degrees. Find an angle that's coterminal with it, which will give you the same answers, but it's smaller. So we can subtract 360 as many times as we want until we finally get an angle that's easier to think about in our head. 120 degrees. Okay, that I can visualize. A little bit bigger than 90. Okay, so finding a coterminal angle gives you an easier angle to work with. So we don't want to work with angles that are bigger than 360. And we also don't want to work with angles that are smaller than, what do you think? 0. Because now we're getting into negatives. In general, we want to try to work with angles between 0 and 360. That's going to be the easiest to kind of think about in our head. So let's practice doing a sketch and then finding an angle that's coterminal, that's positive, and then we'll find an angle that's coterminal and negative. Okay, so let's start with 30 degrees. Okay, we want to make sure we know our quadrants, so when we're referencing where an angle is, we can kind of describe it like by what quadrant it's in. So 1 is in the upper right, 2, 3, and 4 going counterclockwise. Okay. So first of all, it says standard position. Where does that mean the initial side has to be?
On the x-axis.
Yep, it has to be on the x-axis. So there's the initial. Now, where would a terminal side of 30 degrees be? Roughly, yep. It's going to be in quadrant 1. Is it like halfway, more than halfway, less than halfway?
A little under.
Like a quarter-ish. From the initial little.
Third of the way up.
Well, if you want to be specific and describe like a fractional amount, yeah, it's 1/3 of the way, because the quadrant's 90.
Yeah.
So this is 1/3 of 90. So think about where half would be, and just go a little bit less. Maybe that's about 30 degrees. Okay, and let's find an angle that's coterminal and positive and negative. What would be an angle that is coterminal with 30 and positive? Preferably the first positive one you come to, because you can do it multiple times, but just the first one is good. Yep. Yep, 390. And what would be an angle that is coterminal? In other words, it would look just like this one, but going around in the negative direction. Yep.
Negative 330.
Negative 330. Good. Okay, given the choice, I wouldn't want to work with either one of the coterminal angles because the original was between 0 and 360. So I would have just stuck with that. But any questions on that one? Okay. Let's try 145. Okay, no choice about the initial. Where is the terminal side going to be this time? Yep.
Quadrant 2.
It's going to be in quadrant 2. Is it going to be halfway in quadrant 2? A little more than halfway? A little less than halfway? Here's 90. Here's 180. What would be halfway?
135.
135.
A little more.
So a little more, right? So, if we got half, maybe about like that, it looks like a little more than half. And let's find an angle that is coterminal and positive. What's an angle that would be coterminal with 145 and positive? Yep, if we just add 360 to that, we get 505. And an angle that's coterminal and negative, we would just subtract 360. Yep.
Negative 250.
Yeah, just to make sure people know how to do it, just minus 360, just like that. Negative 250. Let's do one more of those. This time, negative 45. That's my initial. Where's negative 45 going to be? Start with the quadrant. Yep. Yep, it's going to be in quadrant 4. A little past halfway, halfway,
Halfway.
or before. Yeah, it's exactly halfway. So think of the terminal side. It's like a line with a slope of negative 1. Yep. And what's an angle that is coterminal and positive? Yep, I heard 315. Good. And how about coterminal and negative? Negative 405. Yep. So any questions on how we're finding these coterminal angles? Now, I'm not saying 315 equals negative 405. No, they're not the same number. What I'm saying is they're coterminal. If you draw them, they will have the same initial and the same terminal sides. But it doesn't mean they're the same number. Okay. All right, so now let's talk about names for angles. What do you call, or what's an acute angle? It means, yeah, it's what? Okay, it's under 90. Also has to be one more thing though. Yep.
I don't know.
It does have to be less than 90.
And greater than 0.
It does have to be greater than 0. Negative 10 is not an acute angle. So it's got to be between 0 and 90. What do we call the angle if it's exactly 90?
Right.
Yep, so that's a right angle. How about an obtuse angle? What's that? Obtuse angle.
It's positive.
Yeah, it definitely has to be positive, so it has to be greater than 90. But it also has to be something else. Diego?
Less than 180.
It has to be less than 180, yes. So greater than 90, less than 180. Now the next definition is going to apply not just to a single angle, but to a pair of them. What do you call a pair of angles that adds up to 90? Remember that? A pair of angles that adds up to 90. Yep.
Is it complementary?
Yep, complementary. And the angles do have to be positive. So if you had like negative 10 and 100, well, negative 10 and 100 add up to 90, but they're not complementary. And what do we call a pair of angles that adds up to 180? Yep.
Supplementary.
Supplementary. Again, they still have to be positive. And they add up to 180. Okay, so these are just different names we can use to classify angles based on their size or what they add up to. Any questions on those names? All right. So negative angles do not have complements or supplements. That's what I just said earlier. Okay, so I'm going to give you an angle, and then I just want you to tell me the complement and the supplement. Okay, 48 degrees. What's the complement of 48 degrees? Yes, go ahead. What is it? 42. 42. Yep. And what about the supplement? Julia? 132. Yep. So that's the complement and supplement of 48 degrees. How about negative 18? What's the complement? What do you think? Yeah, Diego?
There isn't one.
There isn't one. Negative angles do not have complements, and negative angles don't have supplements. Okay. How about the complement of x degrees? Assume x is less than 90, because if x was bigger than 90, it wouldn't have a complement. It's already bigger than 90. What's the complement of x degrees? Yeah.
I mean, would it write it as an inequality because we don't have numbers to plug in, or would it just be?
It's going to be a variable expression, but it won't be any kind of inequality or equation.
Okay.
Yep.
Would it just be x plus 90?
No. Because if x was 10 and you do 10 plus 90, you get 100. That's not the complement of 10. Think they know?
You said it's not an inequality, so it's not like.
No, it's not it's an expression.
Okay.
There's no inequality symbol.
What is like less than 90 degree?
It's a formula you could plug into and it would give you the complement of x degrees. Nico?
X plus 90 minus x.
Well, x plus 90 minus x, that would just be 90. Because it would be, your x's would just cancel out. Yeah. Yep.
Is it just 90 minus x?
90 minus x.
Oh.
The complementary would be 180 minus it. The supplementary.
The supplementary would be 180 minus x. So that's not an inequality. There's no less than or greater than. But it's an expression, variable expression. Any question on the formula for complementary or supplementary? That's basically the general formula, how you can do it. If you have an angle, subtract it from 180 and it gives you the supplement. Subtract it from 90 and it gives you the complement. As long as your angle's not bigger than 90, then you'd end up with a negative, so that wouldn't work. All right, so when we started drawing these angles, we noticed that there was this other number at the bottom. Okay, and sometimes the number is a decimal. Sometimes all of a sudden it changes into something with a pi in it, if you get it just right. And that bottom number is radians. Okay, it's another way we can measure angles. And if you look at the word radian, it kind of looks similar, has a lot of letters in common with another word from geometry. Yep.
Radius.
Radius. So I'm going to use that idea to show you not how to convert between radians and degrees right away, but I'm going to show you a picture of what a radian looks like, something you can visualize. So what we're going to do is we're going to draw an angle inside of a circle. Okay, so what I've drawn here is a circle. The center of the circle is at C. And I've drawn angle ACB. Ray CB is the initial side. Ray CA is the terminal side. Now, those two sides of the angle, they hit the edge of the circle here and here. If I connect the two purple dots together, okay, tracing along the edge of the circle, I get what's called an arc. So arc AB. So any question on my diagram? Now, if this angle was exactly 1 radian, it's a little bit big. It should be smaller. If I want to make it a little more to scale, I could fix it a little bit. That's a little better. That's about what 1 radian looks like. I mean, without getting out a protractor, it's kind of hard to do it exact, but about like that. If this angle was exactly 1 radian, then there would be 2 things on this circle that have exactly the same length. This arc in red and that radius of the circle. That only happens if you draw an angle that is exactly 1 radian. So like if you took a piece of string and you laid it along the arc AB, and then you took that piece of string and you straightened it out, if the length of the arc and the length of the radius came out to exactly the same number, I don't know what that number would be, it depends on the size of the circle, but if they came out the same, then you have an angle that is exactly 1 radian. So it doesn't really help you to convert between radians and degrees, but what it does do is it gives you kind of a visual, and that's pretty close. It's pretty accurate. Okay, that arc in red is probably about the same length as the radius. So is there any question on the connection between the arc and the radius in a circle that has an angle that is 1 radian? Yeah.
Is there certain like angle, like a degree that equals 1 radian?
Yeah, we're going to figure that out. It's about that. It's about 57 degrees. About. It's not exact. Because you noticed when we started doing radians, what was the number when I was dragging it around the circle that all of a sudden popped up a lot? Yeah?
Pi.
Pi. So pi is not a nice number to work with. It has something to do with pi. So we'll look at that. All right, so how do we convert between radians and degrees? Well, the way we're going to figure out how to do it is we're going to draw a circle, but it's going to be a special circle. It's going to be what we call a unit circle. What a unit circle is a circle where the radius of the circle is 1 unit. It doesn't matter, 1 foot, 1 inch, 1 mile, whatever you want, 1 unit. And what we're going to try to do is figure out a connection between a certain number of degrees and a certain number of radians. We already know a connection between degrees and revolutions. 1 revolution, 1, didn't write it yet. 1 revolution equals how many degrees?
360.
360. Because you know that fact, you could convert any number of revolutions to degrees that you want, just by setting up a proportion. Degrees. So you know that in 1 revolution, there's 360 degrees. So let's say I wanted you to figure out how many degrees in 4.5 revolutions. Well, because you already know this fact, you can figure out another fact. Right? I could have put a 4.5 here. I could have put 5.2. Is there any limit to what number I could have put right here? No, I mean, I can't. I could do negative revolutions if I wanted, right? Go the other way. Just because I used a 1 and a 360, it doesn't limit what number I can put right there. But the whole key is that you know how many degrees in a revolution. How many radians in a revolution? Okay, is that from what I showed you earlier?
Yeah.
When I showed you, yeah. Did you know that before today?
God, no.
Okay, so let's pretend like we didn't see that yet. That is right, though. But the problem is right now we don't know how many radians in a revolution. We don't have this kind of starting point that 1 revolution equals this many radians. If we did, then we could come up with a conversion. So I'm going to show you how you can figure out how many radians in a revolution if you didn't know. Now, to figure this out, you've got to know something. We've got to start with some fact. So this is a fact that is always true on a unit circle. And the fact that it's only true on a unit circle doesn't mean it limits us. We're just trying to figure out how many radians in 1 revolution, and we're trying to do it the easiest way possible. So I'm giving you a circle that's easy to work with, unit circle. And the fact that I'm telling you that is true is if you draw something on a unit circle, then the measure of the angle that you draw will always equal the length of the arc. Okay, let's draw an example. Let's say that that's a unit circle, and I draw an angle inside it, like that. And I tell you that that angle is 0.8 radians. That angle is 0.8 radians. How big would this arc be based on this sentence right here? The angle is 0.8 radians. Yeah? 0.8. Yeah. Because the size of the angle is equal to the length of the arc. So if that's 0.8 radians, that arc is 0.8 units, whatever the unit is, inches, centimeters, depends on what you used. What if this angle was 1.2 radians? What would be the size of this arc? 1.2. If this angle was 5.3 radians, this arc would be 5.3 units. The angle size and the arc size are always equal to each other on the unit circle. Okay. All right, so now let's think about making that angle even bigger. Let's say that this is my initial side right here, and then my terminal side went all the way around one time. So now the angle has become so big that this arc now takes up the entire circle. What do we call an arc that takes up the entire circle? Yeah?
Diameter?
So the diameter is the distance across it.
Oh, right,
Yeah. But it's one of those words. Yeah?
Oh,
Yep, what?
would it be circumference?
Yeah. So the circumference. So why is the circumference helpful? Well, if you can find the length of the arc, which in this case is the circumference, if you can find the length of the arc that goes all the way around the circle, it will be exactly the same as the number of radians to go all the way around the circle. Because the length of the arc and the measure of the angle are always the same. You doing okay? Okay. Am I losing people? All right. So, how do you find the circumference of a circle? Yep. Something with pi. And radius is in there too. Yep.
Is it 2 pi times radius squared?
Pi r squared is the area without the 2.
Okay.
But, yep,
2 pi r.
just 2 pi r. Yeah. Okay. So what we're going to do is find the length of the arc that goes all the way around the circle. And that's going to be equal to the measure of the angle in radians that goes all the way around the circle. Because those two things always match on this kind of circle. So we're trying to figure out something that we know, the circumference, and that will be equal to the number of radians, which we don't know, to go around the circle. So in this circle, what's the radius of it?
It's a unit circle,
It's a unit circle.
so it would be 1.
It would be 1. So the circumference of this circle is 2 pi times 1, which is how much? Yeah, 2 pi. 2 pi is the length of the arc that goes all the way around the circle. And what do we know that that's equal to?
Radian.
The what?
Radian.
You say a little bit more? So the length of the arc is equal to, yeah? Well, yeah, yes, that is my circumference. But the circumference is equal to
Radians angle.
the angle measured in radians, yes. So the circumference is 2 pi. So how many radians does it take to go all the way around the circle? Two pi, because the length of the arc and the number of radians to go around the circle are exactly the same. So it's 2 pi units to go all the way around the circle. So it's 2 pi radians to go all the way around the circle, because they have to be equal to each other. So now we know how many radians in one revolution. 2 pi. So how many degrees instead of 2 pi, let's say 1 pi. 2 pi is equal to 360 degrees. What would 1 pi be equal to? 180, because 1 pi is half of 2 pi. It's halfway around the circle, and we know that halfway around the circle is 180. Now, when you give somebody a conversion between units, you could do it that way, but usually you try to make the conversion easier for someone. What number is usually involved in a conversion? Like, how would you explain to me to convert from feet to inches? What would you tell me? Yep.
1 foot is 12 inches.
Okay. How about if I wanted to convert between seconds and minutes? What would you tell me?
60 seconds and 1 minute.
Okay. What number do both of those conversions that you guys just said have in common? Yep.
Both end up equaling to 1. like 60 is to 1, and then 12 is to 1.
Right, you always try to compare something to 1, right? You say in 1 hour, there's 60 minutes. You could tell somebody in 3 hours, there's 180 minutes, and they could figure it out. But it would be easier if you just said 1 hour is 60 minutes. So let's do the same thing here. Let's get a 1 in this conversion, because right now we've got a pi and we've got a 180. We don't have a 1 in. So let's do, which way do I want to do first? Okay. Let's get a 1 on the right side. What could I do to both sides to make the right side a 1?
Divide by 180.
Do what?
Divide by 180.
Yeah, let's divide each side by 180. And then you get pi over 180. Label just stays right there. Nothing happens to that. Pi over 180 equals, and if you divide the right side by 1, you get, I'm sorry, if you divide the right side by 180, you get 1. Yeah. 1 degree equals pi over 180 radians. That's how many radians in 1 degree. Now, what if I wanted a formula for 2 degrees? Okay, I've got a formula for 1 degree. How could I modify this so it says 2 degrees equals? Yep.
Would you add 1 degree at a time? Like, I mean, to get to 1 degree to 2 degrees, you add 1, so it'd be.
So we got to make this a 2. Yeah, we got to make this 2 degrees somehow. Yep.
Multiply by 2.
Yeah, just multiply it by 2. Right? If you multiply each side by 2, now you would have 2 degrees equals, and you got a calculation you could do out. What if I asked you to convert 5 degrees to radians? What would you do to that formula? Times by 5 on both sides. Now the right side says 5 degrees, and the left side, well, we've got something we can type in and figure it out. What you put inside the purple box, that's not important. That's just what you're trying to convert. This is what's important. Whenever you're trying to convert from a degree to a radian, you multiply what you're trying to convert by pi, and you divide by 180. Those are the 2 steps to convert from degrees to radians. Multiply by pi, divide by 180. Those are the 2 steps. What do you think I have right here? Multiply by pi and divide by 180. So that's degrees to radians. And the other way we can go is radians to degrees. Well, for that, let's get a 1 on the left side. How would we get a 1 on the left side of this equation? Luke, can you help us out? How would we get a 1 on that side?
From the right side to the left?
We want a 1 on the left side.
Yeah. When you just divide both sides by 1.
If you divide both sides by 1, it would stay exactly the same. Dividing by 1 doesn't change anything.
Oh, yeah. I mean, subtract by 1.
So to get a 1 on the left, if you do pi minus 1, that's like 2.1.
Oh, I was looking at the equation on there, my bad. Wait, so you get a 1.
It's the same way we got a 1 on the right, but we're just going to do it on the left. Well, that's what we did the first time. Yep, and that got us a 1 on the right. But now we're going to divide by help them out. What do we have to divide by to get a 1 on the left? Yep.
Divide by pi.
Pi. Yeah. Divide each side by pi. If you divide each side by pi, you would get 1 radian equals, and then the right side divided by pi. So if you want to know how many degrees in 1 radian, it's 180 divided by pi. It's about 57. So anytime that you are converting from a radian to a degree, you basically have this fraction involved. 180 is in the top. Divide by pi is in the bottom.
You just do this reciprocal.
What's that? Yeah, it's just flipped. Yep. So when you're converting between radians and degrees, one is multiplied by pi and divide by 180. The other one is multiplied by 180 and divide by pi. And we don't want to mix them up. Okay, so let's try converting 30 degrees to radians. When you're converting 2 radians, what goes in the top?
Pi.
Pi. What goes in the bottom? 180. And if you want to think of the 30 as being over 1, you can. The degree symbol in the bottom and in the top cancels out. How many times does 30 go into itself?
30 into itself.
Yeah. Yep. And how many times does 30 go into 180? 6. Now multiply straight across. What's 1 times pi? Pi. And what's 1 times 6? 6. That's how you write your final answer. And you'll notice the same thing on here. If I go to 30 degrees, it says pi over 6. Okay. Notice they don't put RAD on the pi over 6. When you have an angle in radians, you never label it RAD. Okay. The only time you put a label on it is if it's in degrees. Any questions on that? So we'll practice some more of those tomorrow, but that was the last thing, converting between radians and degrees. So those are the questions for tonight. They're pretty quick. Finding complements, finding supplements, saying if it's a Q, right, or Q's. Pretty quick. Remember that if you ever have to use pi as a decimal, don't use 3.14. Always use the pi button because it's more accurate.